Let's look at two examples where we are going to solve a homogeneous differential equation and an initial value problem. On the left, I've written down 4 steps in purple that we can follow, and on the right, I've written down the 2 general forms for a homogeneous differential equation. Let's look at our first example. The first thing that we want to do is make a change of variables. To decide which change of variables to make, we need to look at the coefficients that multiply dx and dy. The coefficient that multiplies dx we're going to call m, and it is x squared plus y squared. And then the coefficient that multiplies y we'll call n, and that is minus xy. Because m has 2 terms in it and n just has 1 term in it, n is simpler. And that means that we're going to make the change of variables y is equal to u times x. One easy way to remember this is to notice that n is the coefficient that multiplies dy, and that's why y is our new change of variables. Our second step is to differentiate y is equal to u times x. Let's do that. We have y is equal to u times x. We are going to take the derivative with respect to x. Using the product rule, we get u plus x times du dx. So we can substitute this back up into our equation. We need to write this in differential form. So this becomes dy is equal to u dx plus x du. If you're comfortable doing this, you can always just jump from this to this. Step 3 is to substitute this change of variables back into the differential equation. We're going to substitute y that I've already highlighted over here on the right in yellow, and we're going to substitute in dy as well. I'm going to go ahead and recopy our equation. We have x squared plus y squared times dx minus xy dy is equal to 0. Now we're going to substitute these yellow expressions. This gives us x squared plus y squared. Y squared is u squared x squared dx minus x times y, which is ux, and then we have our dy, u dx plus x du, and that's equal to 0. Let's go ahead and simplify this and group all of our dx's together and all of the du's together. This first term we won't change at all. But this next term we're going to multiply out because it has a dx and a du in it. This becomes minus x squared u squared dx minus x cubed u du. And that's equal to 0. Notice that this term is going to cancel with this term. And this gives us x squared dx minus x cubed u du is equal to 0. Now let's go back up and look at our fourth step. That step is to reduce our differential equation to a separable equation and then solve it. To make this a separable equation, we need to separate our x's and our u's. This gives us x squared dx is equal to x cubed u du. Since u is equal to y over x, that comes from right up there, I'm going to switch the sides so that our y will be on the left. You don't have to do that, I just like to. This gives us x cubed u du is equal to x squared dx. Let's put the x cubed on the right, so this becomes u du is equal to 1 over x dx. We can then integrate both sides, and we get u squared over 2 is equal to natural log absolute x plus c. Now let's substitute in that u is y over x. This gives us y squared over 2x squared is equal to natural log absolute x plus c. Let's now get y squared by itself. We have y squared is equal to 2x squared ln absolute x plus c. Now let's go back up to the top again. Notice that this problem was an initial value problem because we were told that y at 1 is 0. Our solution with our constant is the general solution, but we want a particular solution that corresponds to y at 1 equals 0. To get this particular solution, we're going to substitute in that x is 1 and y is equal to 0, and we're going to find c. We get 0 is equal to 2 times 1, so this is 2, natural log 1 plus c. Natural log of 1 is equal to 0, so c is equal to 0. Our solution then becomes y is equal to plus or minus x times the square root of 2 natural log absolute x. And that's the solution to our homogeneous equation. Let's now look at our second example. I wanted to do this problem because I wanted to show you what it looks like when we use the other change of variables. To decide which change of variables to use, let's let m of xy be equal to 2x cubed y. That's just the coefficient that multiplies dx. And then n of xy equals x to the fourth plus y to the fourth. Since m has only one term and n has two terms in it, this is the simpler term. And that means that we're going to use the change of variables x is equal to v times y. In step 2, we are going to differentiate this change of variables. We're going to take the derivative with respect to y. So this gives us dx dy is equal to v plus y dv dy. Writing this in differential form, we get dx is equal to v dy plus y dv. Let's highlight these because we are going to need these. In step 3, we're going to take both of those highlighted expressions and we're going to put them back into our differential equation. Let's write our differential equation down. 2x cubed y dx plus x to the fourth plus y to the fourth dy is equal to 0. We're going to substitute in for x and dx. We have 2, and then we have x cubed, so that's v cubed, y cubed. We have a y, and then we substitute in our dx, v dy plus y dv. And then we add x to the fourth, which is now v to the fourth, y to the fourth, plus y to the fourth, times dy, and that's equal to 0. Let's go ahead and let's multiply everything out. We get 2v to the fourth, y to the fourth dy, plus 2v cubed, y to the fifth dv, plus v to the fourth, y to the fourth dy, and then lastly we have y to the fourth dy is equal to 0. Let's now combine our dy terms, and then we have our dv term. Let's keep the dy terms on the left. This gives us 3v to the fourth, y to the fourth, plus y to the fourth, times dy, and then we'll bring the dv to the right, and that gives us minus 2v cubed, y to the fifth, dv. Let's do one last thing, and let's factor out the y to the fourth. So we have 3v to the fourth plus 1 dy, and then our right-hand side stays the same. In step 4, we are going to reduce this differential equation to a separable equation and solve it. Let's put the y terms on the left and the v's on the right. We have y to the 4th, all divided by y to the 5th dy, and that's equal to minus 2v cubed, all divided by 3v to the 4th plus 1 times dv. Let's simplify our left-hand side. We have 1 over y dy, and then our right-hand side is the same. Now we need to integrate both sides. On the left, we have natural log absolute value y, and then on the right, we have minus 2 times the integral v cubed divided by 3v to the 4th plus 1 times dv. To evaluate this integral on the right, we are going to need to use u substitution. We're going to let this expression be equal to u. So du is 12v cubed dv, and that tells us that v cubed dv is equal to du divided by 12. Let's go ahead and let's put that in. On the left, we still have our natural log absolute y, and now we have minus 2 times the integral du divided by 12 up on top, and then we just have a u on the bottom. This gives us a minus 1 over 6 natural log absolute value of u. And then let's plug in what our u is. Our u was 3v to the 4th plus 1. And then let's not forget to add on our arbitrary constant, and I'm going to call that c1. Let's now do some combining. We have a natural log on the left and one on the right. Let's move both of these natural logs to the left, and we get natural log absolute value y plus 1 over 6 natural log absolute value 3v to the 4th plus 1, and that is equal to c1. In order to combine the logarithms, we need to move our constant inside the natural log. I would prefer to raise a term to the 6th power rather than the 1/6 power, so I'm actually going to multiply each term in our equation by 6. We have 6 ln absolute y plus ln absolute 3v to the 4th plus 1 is equal to 6c1, and let's just call that c2. Now we can combine our logarithms. This gives us natural log absolute value y to the 6th times the quantity 3v to the 4th plus 1 is equal to c2. Since we're running out of room, I am going to take this and I'm going to bring this over to the next page. Let's also write down that v is equal to x divided by y, because we're going to plug that in right now. This gives us natural log absolute value y to the 6th times 3x to the 4th divided by y to the 4th plus 1. Let's now multiply the y to the 6th through, and this gives us natural log of 3x to the 4th y squared plus y to the 6th. And then let's pull back out a y squared. In hindsight, we could have just multiplied by y to the 4th. Now we want to eliminate our natural log, so we're going to exponentiate each side of the equation. On the left, we get e to the natural log y squared 3x to the 4th plus y to the 4th. And on the right, we get e to the c2, and we're going to call that c. On the left-hand side, we then get absolute value y squared times 3x to the fourth plus y to the fourth is equal to c. And then notice on the left-hand side, every term is raised to an even power, so we can drop the absolute value, and we get y squared times 3x to the fourth plus y to the fourth is equal to c. And that's our final solution. And that's it. You now know how to solve homogeneous differential equations by making a change of variables and reducing the equation to a separable equation. You should now be all set to work through some examples on your own. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.